Okay, let's start our third section. So section number 2 basically just went through some knowledge you may already familiar with, but in power system language, starting from section 3, and we'll utilize mainly the phasors concept to model generator transformers in the power system. And then we introduce the per unit system concept to simplify the representation of the network to be prepared for the following sections. All right, so we're going to cover synchronous generators, cover the models for 2 types of synchronous generators, including ceiling pole rotor generators, round rotor generators. Then we move to power transformers, and then we introduce the per unit system to simplify the representation of the power network. This slide shows the picture of 2 types of synchronous generators. So the generators have both rotors and stator. Stator basically means the armature part carrying the connected to the external network. The rotor means the inside, the revolving part, which is driven by turbine. It can be, if it's a hydro power plant, it will be driven by the hydro turbine. If it's a steam generator, it will be driven by steam turbine. So the rotor will have a single winding, which is called the field winding. So it will carry this current. It's a DC current. The current can be from another DC source or from an AC source through the AC to DC conversion. So this DC current will generate a magnetic field. So under static condition, the magnetic field can be constant, but under some transient condition, you can add some control to this field current to influence the magnetic field, which is called exciter. So when you take a 422, so it will cover more about the modeling for the excitation control to influence this field current to make the magnetic field stronger or weaker. So when the rotor is revolving, so usually we consider the like counterclockwise direction to be the positive direction. So the magnetic field will have flux cutting the armature winding, the winding A, winding B, and winding C. So there will be current and voltage induced in each winding, and to power the external system. From the 2 columns, you can tell the bottom row just indicate the external circuit and also how it's connected to the stator winding circuits and field winding circuit. But the top row indicate 2 types of the rotor. On the left-hand side, that is the ceiling pole rotor. The ceiling pole rotor, you can tell the air gap across the rotor will be different, right? So in this direction, you have much bigger air gap, but in the orthogonal direction, you have a much smaller air gap. But for round rotor generator, it also called a cylindrical rotor generator. So the air gap in all directions will be evenly, basically the same, will be evenly distributed. So in any direction, it will about the same air gap. So the round rotor generator can operate at a very high speed. So that make the number of poles to be fewer than the number of the poles for the ceiling pole rotor generator. So in reality, for the ceiling pole rotor generator, it's very rare to see only just 2 poles, because that will create this unbalanced air gap when it's revolved. So very likely, so you will have many such poles, right? So 2 poles indicate there's 1 N and 1 S, and 2 pairs of poles, you may have 2 N, 2 S. So actually, you can have many such poles. And finally, the air gap between the rotor and stator will roughly same, but you still see a difference. So we'll talk about that in the next slides. Okay, so those are the key parts of the generator. So for rotor, we're going to consider a single winding, the field winding. For stator, we have A, B, C, 3 winding to be considered. So if the 3 winding are connected in the balance way, both spatial and also temporal, which means they will have basically this identical winding. They just lay out with 120-degree displacement. So you can use this Y connection to simplify the circuit. For balance condition, you don't have that neutral wear, so that one can be saved. It's similar to the AC circuit we talked about in the previous section. The next thing we want to define is one axis, which is basically just the direction of N. We call that the direct axis or D axis. And we also define another axis, which is leading D by 90 degrees. In the orthogonal direction, we call it the quadrature axis or Q axis. As I said, so the positive direction of revolution will be counterclockwise direction. The angular speed is omega, which is 2 pi f. F is 60 hertz in the US. So there will be this equation to connect the number of poles, which is P, and the revolution speed or singular speed, usually in revolution per minute, and the frequency. So you can tell if I have more poles, I can operate at a lower speed to maintain the same frequency. So we want to maintain this one to be 60 hertz. So for the generator with many poles, the speed can be lower. So what type of generator have to operate at a lower speed? Yes, right, because that pretty much depends on the water flow speed. Even you can put some gear to change the speed, but it was relatively low. But if for gas turbine, it's really revolving very quickly, like jet engine. So the speed can be very high. So you can expect for a gas turbine, pretty much you don't need that many poles. So this pole P can be very small. Usually will take the round rotor generator design. But for hydro unit, they will take a ceiling pole rotor design. Another formula which is convenient to translate from P to N for 60 hertz will be this one. All right, so you can easily derive this second formula from first. Okay, let's show some real picture. So this is ceiling pole rotor generator. So it's different from this concept figure with only 2 poles. So you have to have many poles, but you still can tell the air gap in this direction will be bigger, right? In this direction, even they put many poles, but it will never be perfectly same around this around the rotor. Okay. So ceiling pole rotor generators, they have concentrated windings on poles and non-uniform air gap. So they have a short axial length, which means the dimension orthogonal to the rotor will be in the same direction of the axis will be shorter than the diameter, because they usually operate at lower speed. And the rotor can be much bigger than the round rotor generator, so it has large inertia. So for hydraulic turbines, they operate at lower speed than the round rotor generator, such as in the range from 50 revolution per minute to 300 revolution per minute, because it has large number of poles. So based on this figure, you can count how many poles it has. So it has 26. So if you use 26 pole, so remembering the operating speed, which 7 200 divided by P. So if you consider 60 Hertz, if P is 26, so if you do that calculation, it's about 277 revolution per minute. Okay, so it's falling to this typical range. So smaller hydro unit, the speed can be higher than 400 if the inertia is not very large. To help stabilize the operation of a generator under some contingency condition, assume you have some disturbance near this generator. So there will be maybe either imbalance or suddenly change in voltage or current that may cause the generator to oscillate, to vibrate. So one design with a cylindrical rotor generator will be called damper windings embedded into the rotor, each pole. So damper winding is isolated from either the field winding circuit or stator winding circuit. It's like a squirrel cage design with maybe high resistive material. So if oscillating, there will be current induced in the damper winding. So that damper winding will convert the oscillatory energy into heat that help damp the oscillation. So when that damper winding is not important for this course because we focus on steady state. For steady state condition, damper winding can be ignored. But when you take a 422, if we still come back to the generator modeling, we have to model that damper winding. But fortunately, in this course, we ignore that damper winding. The second type is round rotor generator. So you can see this is a round rotor. It's fitting to this stator. The diameter is much smaller, and axial length is much bigger. So usually the round rotors are used for the steam and gas turbine generator operated at much higher speed. For instance, if you consider 2 poles or 4 poles and use this formula, so the speed will be from 1800 to 3600 revolution per minute. Okay. So it's much higher than the cylindrical rotor generator. But for this rotor, it's hard to design a damper winding inside of the rotor, but they can make some material inside the rotor to create a damping effect by converting the energy of the eddy current into the heat. 70% of large cylinder generators, especially from 150 MVA to 1500 MVA, from round rotor generators. Yeah, because usually the hydro units are only at some locations near the rivers, but you can deploy the steam turbine, gas turbine generator everywhere. Okay, so next we're ready to model the generator, and we start from a round rotor generator because round rotor generator is simpler. It has fewer poles and they have a better symmetry. Later, when we finish this modeling, we can move to the cylindrical rotor generator. Okay, so we have this picture. The outside is stator with winding A, B, C, D. So we use A and A prime indicate the winding A. So A means the current will be coming out from the screen, and A prime will indicate the current is going into the screen. So you can assume there's a winding carrying the current in this way. B will be lagging A by 120 degrees in terms of the current, the peak value. But because the rotor is revolving counterclockwise, so it will align with A first. Then after 120 degrees, will align with B. So B will, in the spatial position, will be 120 degrees leading A. And this is C. Okay. So those are the 3 stator windings. And for rotor, only have just single winding. So the current is coming out from here and going to the screen at this point. So that will make this side to be N, this side to be S. So we can draw the direct axis will be upright direction. and the Q axis will be 90-degree leading B. Okay, so we have determined the axis. So next we want to determine the initial time, okay, which is important because in section 2 we use cosine function as the basic function to formulate AC current voltage. So we still stay with cosine function because we need to write down the expression about how the flux linkage can change. So under static state condition, the field current with the rotor will be constant. It will generate this constant magnetic field, which is like permanent magnet revolving inside. But because the relative angle will be changing along this circle in the cycle, so if we want to estimate or determine the voltage currently induced only in winding A, we need to know how much flux is really coupled with winding A. But right, that coupling will be periodically changed. So in which direction? So this magnet will have fully coupled with winding A. Is this position? Assume the stator doesn't move. Okay, ABC will stay the same, but rotor will revolve at a similar speed. So at this position, the flux is going to this direction, right? But A winding, let's draw. So A winding is something like this way. But flux linkage is going this direction. So for this picture, the flux has no coupling with the winding because it's in parallel with the winding. So which means if we turn the rotor back 90 degrees, so when N-axis is pointing to this direction, the flux is fully coupled with A, right? So in this direction, 90 degrees before, you have the maximal coupling for the flux of the rotor with the stator winding A. Okay, so next we can define initial time. Since we're going to use cosine function to model the flux linkage, which means if we trace back 90 degrees, when ds is pointing this direction, that really be the starting time. So right now, this picture is not starting time. So we let t be 0 when the ns, which is ds, is aligned with the A prime, A winding. So in this direction. So when the D is in parallel with this direction, that is a time 0. So for this moment, that's time when angle become 90 degrees. Okay, so which means the T is 90 degrees divided by omega. This is the current time. This is time 0. For the flux linkage, means the phi here is just the flux generated by the magnet. Okay, N will be the number of turns of the A winding, and the cosine angle determine the relative position. So when t is 0, that cosine omega t has the largest value. So when the rotor is the magnetic field is fully coupled with the winding A. So we can use this cosine function. But if you decide to use sine function to model this flux linkage, so you cannot use you have to redefine the 0 time. Okay, next we can calculate the induced voltage of only winding A. So EA is actually the induced voltage for winding A. For B and C winding, you will have other values. So they will have 120 degree displacement. So based on the Faraday's law, if you know the change of the flux linkage, you will calculate the derivative with the time and then multiply by negative sign, because the induced voltage always try to mitigate the change of the flux linkage. So that's why you have negative sign. So you calculate negative d lambda by dt. So you have omega n and then sine omega t. Okay, so write down in the sinusoidal function will have maximum value Emax. Emax will be the peak value of the voltage induced in the A winding. and the sine omega t just indicate at time 0 when t is in this direction. So the induced voltage is 0, but at this moment that reaches the maximum value. So the induced voltage reaches the maximum at this moment, at this picture, and when the omega t equals 90 degrees. So the RMS value for the induced voltage will be just the peak value divided by root of 2. So it will be equal to this value. So that is the induced voltage peak value. So if you want to know, you want the winding A to generate the RMS value voltage for certain amount, you can use this formula to determine the how many N you need to have, and also the strength of the phi. Okay, next we want to determine the direction of a current. So if we treat the generator as a source and everything else connected to the winding A as the load, the entire load of this generator, so that load will have both active load and reactive load. So it will have both P and Q. So which means the current in the winding A will not be in the same direction of voltage in most of in normal conditions. So very likely the current will be lagging the voltage because most of the load in real world have power factor which are lagging. So we just assume the current will be lagging voltage by a power factor angle psi. Here we use psi just to differentiate from the power factor on the low side because you have the generator deliver power through transmission line to the load. On load, usually we use theta for power factor angle, but on the source side, including the transmission line, we use psi as power factor angle. Okay, so we have to figure out how to draw the direction of the winding A current. If it's a lagging voltage by psi angle, which means if at this moment the voltage has the maximum value, which means if I turn the rotor by another angle, which is psi, and the current will reach the maximum value. So if a further turn by this angle, the current will reach the maximum value, which means at this moment, so we can define one axis, which is always lagging D axis by angle psi. That just help us to determine the peak value of current. So this angle is psi. That's the power factor of everything else outside the generator. So if this is the direction of the voltage, so current will be lagging the voltage by psi, orthogonal to this axis. Okay, so we can easily write down the expression for currents in winding A, winding B, and winding C. So we simply just copy the form of a voltage, and we just put the negative psi as power factor angle. Any question? All right. Okay, so this slide is a very busy slide because I want to integrate everything to the same slide to help you to understand the modeling, the key part of modeling, which is how to determine the phasor for the induced voltage EA. Because here we just draw the EA here as the voltage induced. Oh, that's good. Induced in winding A, but we still need to determine the direction, the magnitude. We don't want to draw this figure every time when we study generator. We want to get rid of this figure, but use much simpler concept to abstract a phasor representing this voltage. Okay, to determine the length of this voltage or the magnitude of this voltage, we have to know what contribute to induce this voltage. So that will be contributed by usually the voltage induced by magnetomotive force. Magnetomotive force means you have current induce magnetic field, and magnetic field will induce voltage. But for the generator, it's a little bit complex because we have currents in both the rotor winding and the stator winding. So both rotor winding and stator winding will generate magnetic force. So we'll start from the rotor winding, which is the field winding, then we go to the stator winding, then we determine the total magnetic force. For rotor winding, that's very simple because this field winding magnetic force, MMF, we call it IFR. It will just revolve together with rotor because this one is simply equal to the number of turns of the winding multiplied by the field current. Okay, so if field current is constant, you know the how many turns of winding you have. This is just IFR. So it will always in the direction of d-axis. But for the armature winding, magnetic force is a little bit tricky because we have 3 such windings, and also the current is each current is alternating. It's not constant current. So if we use instantaneous value, if we pick a winding A, assume each winding will have k turns of the winding. So we'll k multiplied by the instantaneous current A. For the B winding, it will be same k, but you multiply by another current IB. And those 3 magnetic force, the direction is always the same because the winding doesn't change. A, B, C, they will stay the same. So which means if you draw those magnetic force, they will be like a phasor or vector pointing to the same direction, but the value is proportional to the current. So we have to determine the direction. So we already define the direction right now because A is here, right? A axis is pointing to the right. So we have to define the positive axis for A, which is this one. Then B will be leading A by 120 degrees spatially, but temporally it will be lagging by 120 degrees. And C will be lagging A by 120 degrees spatially. So those 3 arrows only indicate the direction in their physical position for those magnetic force due to the armature stator winding, but it doesn't tell the length. We still need to determine the length of the phasor. So what I mean is this dotted arrow indicate the positive direction for FA, but FA is proportional to the instantaneous current in winding A. So which means there's a sinusoidal wave in this direction, but the value can change sinusoidally. Okay, so the other FB also there will be a sinusoidal function changing in this direction, and C is same. So you know, so there's a 3 direction phasors, and the length of each one will change periodically. So we have to figure out, formulate each one, then calculate the total magnetic force. So they totally become something we call it maybe FS, which is stator winding magnetic force. We don't want the FS to be too complex because we're going to need FS together FR to determine the EA, the phasor for the stator winding A. Everybody follow? Or if you lost, just let me know where did you lost. Because we need to make this slide even more busier. Okay, as I said, so then we need to measure the lines of each magnetic force. We have to draw either the current, the 3 winding current, then multiply by K, that will be the actual value of magnetic force. So each one will be a sinusoidal function. Another thing is we have to know, so for this moment showing the picture, that's only when the voltage in winding A reach a maximum value. Because there's another power factor to determine when the current reach a maximum value. So we still need to keep in mind that side, which is power factor angle. So we draw this axis phi, the psi, which is, we call it the MN axis, which indicate when the current will reach the maximum value. Okay, so how do we integrate the three three vectors which are pointing to three different directions and with the magnitude change periodically? How do we determine the total value? So one idea is we assume this phasor, if it's just single phasor, it has two components. One component is in parallel with the MN axis. The other is in orthogonal to the MN axis. Yeah, in the parallel direction, so we project each F onto this direction. So in parallel direction, which means for the FA, so if there's a FA magnetic multiforce of 1 in A, we project to this direction. So you draw this rectangle. So we pick this one. Redraw this. Okay. So we draw we keep the component of FA in the parallel direction. So similarly for FB, if I change the color, make it clear. So for B, for this one, we also find this component, project to that parallel direction. So similarly for the green one, which is FC, it will be this one. Okay, so we have three arrows in the direction of MN axis. So they're all parallel. So we can calculate the sum. Similarly, we do the same thing for the orthogonal direction. So to get those projections, we just need to multiply this waveform by a cosine angle. Each one will multiply by cosine angle. So you just calculate this one. So here you need to utilize one trigonometric identity. Later we'll use the other one. So we're going to use the second one. We'll calculate sine theta multiplied by cosine phi, which is equal to half of the sine, the sum, and plus sine, the difference. Okay, so because here the two angles, yeah, the two angles actually identical. So the difference will be 0. So each item, there are 3 items. Each item will generate 2 items. And the second one is 0 because they have angle same, right? 0, so sine 0 is 0. So second item doesn't exist. The first item will be sum. But when you have 3 sine functions and their angle only displaced by 120 degrees, the sum will be 0. Right? We already know that from the 3-phase circuit. So when you calculate 3 sine functions, the angle will separate by 120 degrees. The sum is always 0. So this is 0. So there's no net component in the direction parallel with MN axis. So you can, so this is the first item is gone. For the second item, we calculate their component in the orthogonal direction. So which means for the FA, so we're going to find this component, and for FB will be about this component, and FC will be this component. So each one will multiply by cosine angle, or sine angle, sorry. And then we utilize the first formula. But for the first formula, and when we calculate the difference between the two angles, so this will be 0. So we have a cosine 0, cosine 0, cosine 0. So cosine 0 is 1. And each one, 1 multiplied by half will be half. So we have 1 half and second half and third half. So we have 3 halves. But for second item, we have the sum of 2 angles. So the sum of 2 angles will be sum of double this angle and double this angle and double this angle. So 3 cosine functions with 3 angles also split by 240 degrees, which is equivalent to be to separate by 120 degrees. So second item all cancel. We only have the first item, 3/2. So that sum will be 3/2 of the peak value of the magnetomodule force. So finally, the total magnetomodule force, no matter which direction it's pointing to, always have the same value. So if this is constant, so this one will be constant. We'll have a constant magnitude under steady state condition. And the direction is orthogonal to the MN axis. Okay, just give you an idea on what they may look like at 3 different moments. Let's pick this one as the first moment, because we know the positive direction and we know the magnitude value of each f. So we can draw them in the figure and try to determine the total f. So for this moment, first that angle, the direction of the MN axis is 90 degrees. So which means this MN, so right now this is MN axis, right? That determines when the current reaches the maximum value. So we further turn it until it becomes vertical to the ground. So this is 90 degrees. So if this is 90 degrees, and we keep the FA, FC, FB, the direction to be the same. We don't change those directions, but we determine the lines of each arrow based on this figure. Because for this figure, at 90 degrees, FA reaches the maximum value. You have the full length of for this vector. But for the green one and blue one, they become negative. It's about negative. They will have a negative value, which means if this is positive direction for blue, and the FA will have will point to the different direction, opposite direction. Similarly, for the FC will be pointing to opposite direction. So total will give you this FS pointing to the right. So you see that's orthogonal to the MN axis, right? There's a 90 degree. For second moment, we have the green one reach the minimal value. And the red and the blue have positive value, smaller than the maximum. And so the MN axis is in the direction of 150 degrees. Okay. So that total will give you this FS, which is still orthogonal to the MN axis. And the third moment, we have a blue one reaching the maximum value, and we still have the total magnetomodule force orthogonal to the MN axis. Okay, so we can conclude. So the total stator magnetomodule force FS, which is sum of the 3 magnetomodule forces from 3 different windings, spatially separated by 120 degrees, and also the value is changing periodically. But when we calculate the sum, it has constant amplitude and always orthogonal to the MN axis. The MN axis is angle psi, which is power factor angle of this, whatever the generator sees for the rest of the system, lagging the D axis. Okay, let me summarize that. So if you know the D axis for the rotor at any moment, there's a power factor for the load of the generator that determines the psi, angle psi. And then you determine this MN axis be lagging D by psi. Okay, then the total magnetomodule force will be orthogonal to this MN axis by 90 degrees. So if we draw, that will be this one. All right, so so far we have 2 magnetomodule forces determined. So IFR is easier. IFR is always in the same direction of D. FS is orthogonal to the MN. MN is lagging D by psi, which means FS is lagging D by 90 degrees plus psi. Okay, how many follow? Good. Yeah, but at least you believe me, right? So after the class, you can go through either the video, the slide to try to understand what we did. Okay, so great. So now we are ready to give you the phasor diagram. Once we generate the phasor diagram and also the equivalent circuit for generator, let's forget about this figure, right? We don't like this figure. It's only the only value of this figure to help us to understand why that equivalent circuit can make sense. So let's start from a very simple condition when the stator current is zero. So it doesn't connect any load. Okay, it's open circuit condition, no load condition. So that easy. So Fs will be zero. There's no current. And so the rotor winding magnetic force is still equal to the N multiplied by the field current. So itself produces no load voltage. Okay, so we can, if we draw this FR, same as the DS's, and this voltage, the EA will be, for this case, will be induced by the FR. So it will be 90-degree lagging FR. So the E is in the direction of QS because this 1A voltage reached the maximum value when the axis of A is aligned with Q in the direction of the horizontal direction. So we have explained in the previous slide. So we have the two phasors, FR and E. And for condition with load, we have non-zero three-phase current IA, IB, IC. The Fs will not be zero, but it's orthogonal to the Mn. Mn will depend on the load, right? When the external load change the power factor, the Mn can also change. So Fs will be orthogonal to Mn, will be lagging D by 90-degree plus sign. So which means we can draw this Fs as a phasor. So if there's a voltage induced by Fs only, so that is 90-degree lagging Fs. So this is called E armature, means it only just induced by armature winding, not field winding. So finally, we are going to, this voltage induced by rotor only. This voltage induced by stator only. So we're going to calculate the total voltage. That will determine the real voltage you can have for the external system, right, to operate, to be powered. So the sum of the FR and Fs give you the total magnetic force. We call it FSR. So we draw a phasor. So if you see this parallelogram, so that will be the sum of the two magnetic force. So this is the real magnetic force when the system has load. This one will induce some voltage. So that voltage will become the true voltage source of the external system. So that will result in the voltage induced by this one. We also have 90-degree lagging the magnetic force. So far we have three F, right? We start from FR. This one always there, even the system has no load, because as long as you have field winding current, this one will be this value. So this one induced voltage. Even with no load, this voltage will be there, which is like you have a DC battery. Even if you don't connect the battery to circuit, if you measure the voltage on the both terminal, you still have a reading. Right? This is the voltage. And this voltage is induced by the stator winding only. So this is smaller. And the total will be this voltage. This is the true voltage you can utilize as a load. So we have this relationship. So because this E is longer, okay, this E is like on the left-hand side is like a source. It's like DC generator, but sorry, DC battery, the voltage without connecting to any circuit. And this is the voltage you can utilize. This is voltage you can utilize, and this is like voltage due to the stator winding. So when the stator winding have non-zero current, this will be non-zero. So that will generate this voltage that actually reduce the length of E. So this one is always, the blue one is always shorter than the purple one. So which can be shown by this item. So that can explain why, let me see. Yeah, that can be explained why the ESR shorter than the capital E. Okay. So if we want to make this longer one to be the internal voltage, because we want to, our goal is to have the generator modeled by some equivalent circuit. So this internal one will be E. So that doesn't change with the external load, because why the terminal voltage can be different, because they may have some internal impedance of the generator. Okay, so E will be constant, but when the current increase, which means the load increase, so the voltage on this side may be different. That is because we have some internal impedance. We want to model that internal impedance. So that E will be the constant one, only depending on the field current. So we just create another phasor opposite to the armature winding induced voltage, because we want to interpret this E to be the terminal voltage plus some voltage drop inside of the generator. Okay, then we draw the current in the same direction of FS. Then we just define a reactance. The reactance will try to interpret what happened here. It's voltage drop inside of generator. It is because of the current on some reactance. So if the generator inside there's some reactance, like this one, this Z will be contributed by some reactance. That reactance carry the current will create a voltage drop. So that explains why the terminal voltage of generator can be smaller than the internal voltage, the inside voltage. And further, you can also add the resistance and some leakage reactance for perfectly designed generator. That one can be ignored. But when there's air gap, so some flux linkage is not contributing to those voltages will be lost. So you can also add that part. So that will make the impedance, what we're going to model will be, right? We'll have armature winding reactance explaining the voltage drop inside of the generator, and also the leakage reactance, then plus resistance. So this one can be determined. Okay, so let's. Okay, so first we rewrite this equation, and we replace the negative armature winding induced voltage by the voltage drop by some reactance. So the next we also add the voltage drop on the resistance, on the leakage reactance, and V here is the final voltage connected to the system. So this is the equation we are looking for, okay? And next, we can simplify the last two items. We just simply call the total reactance as XS. That is equivalent total internal reactance, okay? We call it a synchronous reactance. Right, so now you know we have this circuit. We have internal voltage E, which is proportional to the field current. So if field current constant, this one will be constant. So if you change the field current, increase or decrease, this one will be changed. But under static condition, this can be remain the same. Then it will go through internal impedance. Internal impedance will have resistance and reactance. The reactance is called signal reactance. Then the terminal voltage will be V. So then we finish this phasor diagram. So see what happened. So there's an internal voltage E. Okay, the first has voltage drop due to the armature winding, due to this SAR, and due to leakage reactance, then due to the the resistance, and then we'll give you V. V will be the real voltage you can measure at terminal in the operating condition. So this table just summarizes the three conditions. So if IFR is leading FS or leading the FSR, so which means that's a generator mode. If IFR become lagging this one, if this one is leading, that's a motor mode. If it's zero, that's a synchronous condenser mode, because this direction determines how much IT power you can deliver. Okay. All right, so we stop here and we'll continue on next Monday.
In candidates, you're able to go to like where the textbook is for the course, and you're able to click on that textbook and you're able to read it.
Yeah.
When I go to click where the textbook is, it's available, but I can't go into it and read it. Is there any way that you can make